Okay, so last time we talked about the Boolean logics. Okay, so the Boolean logic basically is a kind of area in. Okay, a Boolean logic is a kind of area in math that discuss some kind of you know statement, whether the statement is true or it's not true. So so mathematicians believe that so somehow they can you know resolve all the problems in our society with math. Uh, it's kind of true in from some perspective, but it's not completely true. So there are some problems that you cannot solve with math, but definitely the Boolean actual logic can solve many of our problems. In the Boolean logic, they basically assign a value to an expression, like a statement, whether the statement is true or not. And then they can use some kind of operations to combine the statements from a single statement to a very complicated statements. Okay, so some of the most important operations are we called uh, and uh, we sometimes it's called a conjunction or disjunction, or we call it or, and then negation. So we use not. Okay. Now these are three different operations that they use to, you know, in a combine couple of simple statement into a more complicated statement. Okay. And then so they also, you know, people also use some other symbols to represent this. And negation can be one horizontal bar, then the vertical bar. And then when the topic was actually discussed, then people find out, then this Boolean logic can be applied uh, to the area in electronic, you know, uh, you know, electronics and in the double E area. So then they actually use some other notation. They use asterisk to represent and use the, oh, I'm sorry, uh, yeah, asterisk, and then use a plus to represent or operation, and sometimes they use tilde to represent not operation. So that's kind of history over here. We discussed that the Boolean algebra is an algebra for manipulation of objects that can take only two values. Um, this value could be either true or false. Okay, so any kind of statement can be true or false. Okay, now in electronics area, so people just find out, we can use some other values, not just the true or false. We can use like in electric, then we can use on and off. So if you, it's just like actually you actually operate on a switch, then you can turn the switch on, turn the switch off. So you can actually say, well, I can use on to represent true, I can use off to represent false. So in this case, I can create some kind of electronic device to simulate these Boolean algebra. So that's basically what it is. So and then, you know, when you apply this concept to the switch, then you can use on and off. And then that means the on normally means, you have actual electricity actually flowing in the wire. Off means actually there's no electricity, in the wire. So there's, so you can use the on and off. So that means in some case you can use the voltage, like high voltage and a low or zero voltage. Okay, so there's no voltage. So when you talk about the electricities, then you have a electric electrical flow in the wire, and then you have no electrical flow. Okay. So in that case, then you can simulate some kind of some kind of electrical flow in the digital circuits. Okay. To make it simple, we actually use 1 to represent the high, 0 represent um, 0, or 1 represent true, 0 represent false. Okay, so that's basically a little bit of history here. So that says that we can actually create some kind of electronic devices to simulate these, Boolean algebra. So, and because we use 1 and 0, so many times we call these devices digital circuits. Okay. Now, in modern days, the digital circuits could be electronic device, or that integrate the circuits that which contains millions or even billions of electronic switch inside these silicon component. Sometimes it's a very small piece of silicon components which contains millions or billions of electronic switch inside. Okay, so they integrate all these electronic switch inside a very small piece of silicon components in there. So, and then these components has some inputs, okay, and also has some outputs. So the input's going to be, for each y, it represents an input. Then if we apply some voltage in there, that represent that we apply 1 to this particular actual input, and then we can apply 0. That means there's no voltage. 1, there's a voltage. 1, there's a voltage. 0 means no electricity. So you can actually use 1 0 1 0 like a sequence of binary digital values to simulate an input. And then these inputs are going to go through all these different switches inside the circuits. And also this could be an input, like a 1 0 1 1 0 0 1. And then these inputs then will be actually computed and eventually generate an output. The output could be a different sequence of values. Okay. So that's the digital circuits. Okay. So now with the digital circuit, then we can use the Boolean algebra to simulate, the operations for these digital circuits. Okay. Now, one of the examples we talked about was this. Let me actually switch back to the PowerPoint. Okay. So we can have, a couple of variables in the we can have a couple of variables like x, y. Okay, x, y's are two variables, and the value for these variable could be 1 or 0. Remember, this is actually a Boolean algebra. So the variable can take a value 1 or 0. So if you have two variables, x and y, the x could be 0, y could be 0, and x could be 1, y could be 1, x could be 0, y could be 1, x 1, y 0, 1, 1 for both x and y. So you can actually like a simulate some kind of circuit that you have 2 input, x and y, and then you have a 1 output. Okay, so one of the operation could be defined as, AND operation. So that means when you apply 0 to x, 0 to y, that means you apply no voltage to x and y. If this is an AND operation, which is basically we use the asterisk, in this case it's not a multiplication, it's an AND operation, then you can generate output 0. Now if it's 0, 1, then you can generate output 0. And 1, 0, you generate output 1, output 0. Now, until you have actually 1 and 1, then you're going to generate output 1. So this is actually kind of operation we can define. Now, and then same thing for the OR operation. This is actually negation. So you have 1 input, 1 output if it's a not operation. So if it's x, then x is 1, then output tilde x is 0. Okay, if x is 0, then output is 1. Now, these operations, AND, OR, and negation, they have some certain kind of a precedence, just like the arithmetic operation, like addition, subtraction, multiplication. There's a rule of precedence. So if you have a couple of operations in the same expression, then you need to figure out which operation is going to be performed first. Okay. Now, in this case, the precedence for these 3 operations is the not operator has highest priority, and the AND operator has the second highest priority, and the OR operator has the lowest priority. That basically says if you have an operation expression like A plus B times C, then you can figure out, well, there's no actually not operator. So then we can take a look at the next one, and there's a 1 AND operator. So you can actually evaluate this one first. Okay, and then once you got the result, then you can evaluate A plus that result, and then you get the result. So in this case, this is actually equivalent to A plus B, and C. Okay, so this is equivalent because this one has a higher precedence than this one. Okay. Now, sometimes if you say, well, if I do want to have to perform the first operation, A plus B first. Now what you do? So then you can use the parentheses. Okay. So then you can say, okay, I want to perform the A plus B first. You use the parentheses and then times C. So then you can perform this operation first, and then perform the AND operation next. Okay. So that's basically the general things. So this is basically the answer. So if A is 1, B is 0, C is 0, then you got the, B is 0, C is 0, 0 and 0, that's 0, right? That's 0. So A is 1. So 0 and 0, that's 0. And then 1 plus 0, that's 1. Okay. Now, if you really want to actually perform the A or B first, or A plus B first, then this is 1, this is 0, this is 0, then 1 plus 0, that's 1, okay, and then times C, 0, so that means 1 and 0, that's give you 0. So you got different answer for this. Okay. You don't have to put the parenthesis on this if you want to actually perform this operation, but if you really want to perform the plus first, you have to put the parentheses because the result is different. Now let's actually work together on this one. Okay. So suppose f is a function which contains 3 variables, x, y, z. Remember, x, y, and z are the binary variable, which means they're going to take only 1 and 0. Okay. So then the operation is x plus tilde y times z. Okay. Now tell me first, which operator going to be performed first?
Negation.
Negation.
Okay, so this one going to be the first, right? So you're going to actually perform this one first. Okay. So because the value of now, so let's actually, so we want to construct a table for this particular function. So you can actually represent a function using a formula, but also you can represent a function using the table. It's called a truth table. Okay. So now because you're going to actually perform the negation of y first. Okay. So then so you can actually perform negation of y. So y, the value for y in each case, you have to, because you have 3 actually variable, so x, y, z. So you're going to actually think about all the possible combinations of these 0 and 1s. So you can have all 0, and then x, y both are 0, and z is 1, and then 0, 1, 0, 0, 1, 1, 1, 0, 0. So you can actually think about all the possible combination. So because you have 3 variables, there are a total of 2 to the 3 possible different combination. So that's basically you have 8 different combinations. Now let's take a look at the negation of y. So because in this first case y is 0, so negation of y is 1, 1, 0, 0, 1, 1, 0, 0, right? So then you can actually now let's next see what's the next operator. Okay,
And
that's the end, right? So you're gonna actually perform this one first. So now tilde y is 1, z is 0, so
0.
1, 0, that's 0,
0.
1,
1.
1, that's 1, right?
0.
0, whatever, it's always 0. That's also 0, whatever the second value. So that's
0.
1, 0, 1, 0, that's 0.
1.
1, 1, that's 1, because C is 1. Okay. Z is 0. 0, that's 0.
0.
0, 1,
0.
that's 0. Okay. And then you got the values for negation y and the z. So then you can figure out the last one. So now x is 0, so plus 0, that's 0. Now in this case, if x is 1, then the result is always going to be 1, right? Because that's the natural of the OR operation. If one of the operand is 1, then the OR operation is going to give you the result 1. So if x is 1, then it doesn't matter what's the second item. It's always 1. Okay. Or if the second item, the negation y times z, if this is a 1,
I'm
then
sorry to interpret, but then the last second column should be 0, because when there are 2 zeros, then it will be a 0. There is no 1 in it.
the last one, you think?
The last second.
Last second. Why? Because x is 1.
X is 1. Yeah.
Okay.
So it doesn't matter whether this second one is 0. So in that case, it's a 1 plus 0. It's still 1.
Okay.
excuse me. That's why I'm saying, because x is the value for x is 1. So that means x is 1, then the result always going to be 1. That's the nature of all operation. Or the second item is 1, then the result is 1. So in this case, this is 1. So the result is going to be 1, right? Now the only scenario is when both x at the second item, and both of these are 0. So x is 0, and this is 0, and then you give you 0 plus 0. That's 0. X is 0. Now this is 0. 0 plus 0. This gives you 0. So basically you got the 0, 1, 0, 0, 1, 1, 1, 1. It's kind of a very strange result. So any questions on this? Okay. So that's one of the examples we worked on. Now, when you actually write any Boolean function or Boolean expression, now, so in this particular case, you know the precedence of this operator, but if you actually want to make it clear, you can always use a parentheses to make it less confusing. For example, you can always put something like, write something like x plus that's okay, because then people, when people see the parentheses, they always evaluated. Oh, sorry, that's the second one. C. They always put, calculate the expression inside the parentheses first, and then do the operations outside the parentheses. So it's the same, okay, but it's always kind of good practice to put the parentheses, even though the precedence always actually defines the orders of the operators, but sometimes people just want to make it actually less confusing. So put the parentheses would be a good idea. Okay. So we have two actually more problems: f of x, y, and f of a, b, and c. And I would like you to actually practice all this and build the truth table for that one. Let's actually work on the first one. Okay, let's work on the first one, because the table is actually smaller for the first one because we only have x and y. So when we build the truth table, we only need to think about x and y, right? So when x is 0, y is 0, x is 0, y 1, y 0, 1, x is x 1, y 0, and 1, 1. So I want you to actually spend time and build this table and just tell me what's the final result for these. Okay, I gave you like a 4 minutes or to 5 minutes. So yeah, just do it. Okay. So so that's the final result. And then you can actually create some intermediate value, because depending on which operator going to be performed first, you can actually perform part of the expression and eventually, build this final result. Okay. So that's the final result. So I want to know what's the final result, but you can always build an intermediate value. Okay. Okay, I'll give you 5 minutes so you can work on this. Yeah, just do the first problem.
It's 1001.
Okay, I think I see a couple of answers here. It's 1, 0,
1001.
0,
Yeah,
1,
1.
right? Okay. Let's just actually verify one of these. I'm not going to verify all of these value. So let's see. Suppose I just check this second value. X is 0, y is 1. So in this case, you need to figure out what's the tilde of y. Okay. So in this case, 0. And then tilde of x, 1, right? So then you can say x plus tilde y, because you always actually execute the negation first, okay? And then you're supposed to actually do the AND operator first and then the OR operator, but because the OR is actually inside the parentheses, so in this case, you need to operate the OR operation first. So x is 0, y tilde y 0, so it's a 0 plus 0, that's 0, and x, tilde x plus y, so that's 1 plus 1, that's 1. Okay, so then the AND operation, 0 and 1, yeah, so it's a 0 and a 1, which is 0. That's correct. Okay, yeah, I think the answer is correct, so we just verify one of the answer. Cool, that's great. So now the following table basically lists all the Boolean, most of the Boolean identities. Okay. Now we have a name for each of the identity. You know, so one of the identities called identity law. Okay, so identity law says if you have an AND operation and one of the value is 1, so then if you have 1 and x, then the result going to be x. because if it's 1, then whatever the second value is, if x is 0, you got a 0. If x is 1, then 1 and 1 get 1. X is 0, you got a 0. So x times x and 1 and x is x. Okay. Now, the identity law actually in the OR form, this is called the AND form, that the identity law applied to the AND operation. If the identity law applied to the OR operation, this gave you this result. So which says if 0 or x, the result is always x. So that means if x is 1, then 0 or 1 is 1. If x is 0 and 0 or 0 is 0. So x0 plus x is always x. Okay. 1 plus x is always 1. Okay. Now the other law is called the null law, which means for the AND operation, if one of the operand is 0, then the result is always 0. It doesn't matter what's the second value, you know. So same thing with this OR form. So if 1 or x is always 1, because the OR operation basically says if one of the operand is 1, then the result is always 1. Okay. Idempotent law, which means x and x is x. Okay. And x plus x is always x. So you can, now how can you verify this? You can basically verify this by check all the possible value for x. So in this case, you can check, if x is 1, if x is 0, then 0 times 0 and 0 is always 0. 1 and 1 is 1. So that means, yeah, if x is 0, x is 1, then you always get this result. And the same thing with this. 0 plus 0 is 0. 1 plus 1 is always 1. So this is always true. Okay. And the inverse law basically says x and tilde x is 0 because, why this is true? Because it doesn't matter what is the value of x. One of the value, x and a negation of x, one of the value must be 0, right? So if one of the value is 0, then the AND operations always give you 0. So if x is 1, the negation of x is 0. So 1 times 0 is 0. If x is 0, then the negation of x is 1. So 0 and 1 is 0. Okay. Now the OR form give you this x and it's the same, but this is true for the same reason, because one of the operand x or negation of x is 1. Okay. These always give you opposite value. Okay. One is 0, the other one is 1. So there's always a 1 operand, so the result always going to be 1. Okay. Now here's a commutative law, so you can switch the order for the AND, and you can switch the order for the OR. And this is associative law. So some of these laws looks like arithmetical law, right? So it works fine. This is called a distributive law. This one is easier to understand. This one, it takes time to understand this one, because now x, AND and OR operation are a kind of, equivalent. It's just a different one. So now in math, this is not true. Only this is true. The second one is true. But in the Boolean, expression, this is also true. Okay. And absorption law, which means if you have x and another expression, the other expression has x inside, then you can actually eliminate the second one, absorb the second one, so you only get the x. This is kind of interesting, right? And also, if x plus x times y, then it's x. Now this is De Morgan law. I remember that we actually proved this De Morgan law using the proof technique, like a proof by contradiction, right? Also, you can also prove this by the truth table. You can build a truth table. So all these Boolean identities, you can always prove. So the left side is always the same as the right side. You can build a truth table on the left side. You can build a truth table on the right side. You will find out the truth table going to be the same. So then you can build this identity. And the double complement law basically means, so if you have an x, then negation of x, and you put another negation of x, then it's back to x. It's very similar to like in math, like you have a negative x, and then you can put another negative, and two negative makes it positive. So it's not the same concept, but it looks like it's the same idea, right? But just make it easy to remember this. Okay, so these are all the identities. Now, if someone asks you to prove any kind of logical expression, may prove two of the logical expressions are same, you can use this. You can use this any of these Boolean identities as the truth. You can always use them. Okay, you don't have to prove it because it's already proved. This is always true. So when someone just tries to say prove that these two actual Boolean expressions are the same or identical, so then you can actually apply these using any of these the Boolean identities. And you don't have to prove this. You can just directly use the result. Okay. One of the most important operations in activities in the Boolean algebra is the simplification of the Boolean expression. Okay. So why I want to do this? So we're going to talk about this a little bit later, because one thing is that if you have two actual Boolean expression, one is simpler than the other one. Okay, both actual Boolean expression going to eventually give you the same truth table. Then which one you prefer? Of course, the simplified one. You always actually like the simpler one, right? You don't want actually the complicated one. So we need to study this. The algebraic identities we study in the algebra class allows us to reduce the algebraic expression to the simplest form. And we can use some kind of a technique to, we can factor the algebraic expression. You can multiply out, you can factor it, you can do whatever the technique you use to simplify the expression. But same thing, you can do this in the Boolean expression. Now one of the question is, it's always confusing and it's always less clear. What is the simplest form? Okay. Now this is kind of actually interesting question, because now I give you two actually Boolean expression. Now I want you to answer which form is the simplest form. Okay. Now we have some kind. Later on, we're gonna discuss about this, and we can actually even give you the answer for this. But at this moment, I want to actually skip this. Basically, we can use our common sense because if you actually your form use less variable, less operator, that's the simpler form, right? So in general, it's hard to define this. We don't, and so unfortunately, there's no defined set of rules for using these identities to minimize the Boolean expression. Okay. So when someone asks you which is the Boolean which can you say it? I gave you a Boolean expression. Can you say this is already the simplest form, which means I cannot simplify even further? Or we still have a room to simplify it. Now, what's the best way to do it? Is there any kind of procedures to do this? And the answer is no for this. Okay. Most of this is based on the experience. Okay. Now we're going to discuss this later when we use when we apply the Boolean algebra into the digital electronics. Then we can actually define, how can we say this form is the simplest form? Okay. So we will discuss this further after we introduce the new concept of the electronic gates. So which is used in the digital electronics. Okay. So so technically, there are an infinite number of Boolean expressions that are logically equivalent to one another. So now to prove the equality of two Boolean expressions, you can simply use the truth table. If two actually Boolean expressions give you the same truth table, then they're equivalent. Okay, so it's very simple. Okay. However, there are many of them, and then to find out which one is the simplest one, it's easy to do it, but not easy to prove it, because there's no actually theoretical way to actually prove that this is the simplest form and this is not. Okay. So, for example, okay, I can ask you to prove that the two Boolean expression x plus y parentheses times tilde x plus y. This Boolean expression is equivalent to y. Okay. Okay. Now, why this is the case? You can prove it. You can build the truth table for this expression. You can build a truth table for this expression. And then if I ask you which expression is the simpler one, it's easy to say, right? Of course, this is simpler, right? So it's easier in practical. It's easier to identify which expression is easier, but it's so difficult to express it theoretically. So you can prove this using two approaches. You can build a truth table, or you can use the Boolean identity. You can always use the Boolean identity to prove it. Okay. So to prove this using the Boolean identity, I think there's a way you can do it, right? You can easily prove it. What's the easiest way to do this? Which particular law you can apply in this case?
X and Y.
Okay. I think one of the approach you can do is, okay, so X and Y, you can write Y plus X, right? That's why this is true. That's associate, that's the community law, right? So you can always exchange the order of X and the Y. Y plus tilde X. And then that's called commutative law. So you can take a look at the
as per null law, anything with x is equals to the other thing. So y plus x is equals to y, the first parenthesis. Then we can resolve the next part of the
Okay.
equation.
There's many different ways. Okay. I think the easiest way is to use the distributive law.
Distributive law.
Can you see that one?
Yep.
Okay. If you use distributive law, that means it's a y plus x times tilde x, right? Can you see this one? That's a distributive law. If you use the distributive law in the end form, in the column in the middle.
Yes.
Okay. Now x and tilde and the negation of x, that always gave you 0, right?
Yes.
Okay. This gave you 0. So that's a distributive law. Okay, I can say distributive law.
Then identity law.
That's identity law. So this give you y.
Y.
That's one way. Now, of course, I hear someone say that in here, you can always multiply in there. So then y times the y plus tilde x plus x times the y plus tilde x. And the first one, you can use the absorption law. So this gave you y. Okay. Right? And the second one, you can say x times y. So this gave you, this first one gave you y. The second one, this one gave you x times y plus x times x tilde x. That gave you 0. And this one used absorption law again. This gave you y. You see that one? Okay. Sometimes it's easy to see it. Sometimes it's not easy, but you can always apply. But the other way you can do is, if you feel like, wow, I don't want to use all these laws, I can just simply build a choose table on both sides. That's the other way to prove this is true. Okay. Now let's actually talk about the other one, the computer transistors and the gates. Okay. So now why we can use the apply the algebraic, the Boolean algebra into the modern computer actually circuit. So let's actually talk about the computer transistors. Now, if you're a WE major, then it's probably a very simple topic for you. So let's say a modern computer is made up of millions or even billions of something called a transistor. Okay. Now, these transistors work as switch that has two states, on and off. But as we say, that these transistors are electronic switch. It's not the switch that we control the light. So you have to manually, switch to on and switch to off. It's basically based on electronic, it's basically on actually, controlled by electricity, electronically controlled. So these are called electronic switch. Okay. Now, when a transistor is in an off state, it does not allow electricity to flow, and when it's on state, electricity can pass unimpededly. Okay. Okay. So from this sense, a transistor is just like a light switch, but it's controlled, electronically, not by hand. Okay, manually. Okay. So the integrated circuit is basically built actually with millions of these transistors. They built into the silicon wafers. And using modern technology, people can build more and more transistors into a very small, integrated circuit. Okay. Now, these integrated circuits are so, powerful that you can actually build billions of transistors in a very small piece of integrated circuit, just like this size. Okay, so that's why. So these actually switch transistors are so close. So the distance is only just, you can measure distance using nanometer. So that's why now people use some kind of nanotechnology to, they're so close, so they are actually at the nano, meter distance. It's not like a millimeter, micrometer. It's nano, or millimeters. It's just nano. It's very so small. Um, so they're very powerful, but they're small. Okay. So if you actually try to actually draw this using the diagram, then the computer actually transistor, can be represented using this diagram. So you have 3 lines for each of the transistors. Okay. Now you have a baseline. That's called a baseline, and the input line and the output line. Okay. That's the input line and output line. Okay. So this is also the control line. So if you put the control lines, then you can actually, if you think about this like a switch, then you can switch it on and switch it off. Okay. So you can actually, or can switch it off. You can disconnect between here and here. Okay. So you can actually switch it on and off using the control line. So this is actually a very simple single transistor, how it actually works. Now next thing is that these transistors are very important in building the computer circuit, the circuits. Okay, the electronic circuits. However, these transistors are small. They can perform a very simple operation, but they're too simple. So that's why people try to use these transistors to build a little bit more complicated circuits. These circuits are called gates. Okay, so so let's take it this way. So if you actually think about a computer as a brain, human brain, okay, then these transistors made up of these computers would be the cells, like a brain, and the brain is made of a small biological cells. Okay, each cell has its own small structure, and each cell has some kind of life there. So all these millions of cells build together to build some kind of biological organ, and then build a brain. Okay. So, but as I say, these cells are too small. Okay. So they may not perform any meaningful functions by themselves. So that's why the real significance of this transistor is that we can easily put a few of these transistors together to build an electronic device called logical gates. Okay, or we call it gate. Okay, so these a gate produce the output of Boolean operation defined by truth table for AND, or, and not operations. Okay, discussed before. This is very nice, right? So now we can build a gate. So the gate gonna be able to simulate these Boolean operation, the logical operation. Okay. Now, besides this AND, or, and not gate, there are some other gates that can perform different Boolean operations. one of the gates is called exclusive OR. Okay, NOR gate or NAND, which is a other than the AND gate, it's a NAND gate. Okay, AND gate or NAND gate. Okay. So now these gates, so it's a kind of small element that can perform some meaningful operation. Okay. Now, so in EE, we normally use this symbol to represent these different gates. So one thing we can build is called NOT gate. Okay, the NOT gate actually going to perform the NOT operation. The AND gate will perform the AND logical operation. NAND, it's a negation of AND gate, so it's kind of AND. It's a negation of, so it's AND basically means negation. So AND NAND. Okay, NAND and AND is basically only difference is that it's the negation of the AND operation. Now, in terms of a notation, we use this to represent the AND gate. And the NAND gate is the same as AND gate, but there's a small circle over here. Okay, so here's the OR gate. You see the difference between AND gate and the OR gate. Okay, the AND gate is just like well, it's just like a rocket. One of the rocket has a actually round head. The other one has a kind of excuse me, angle here. So this is the OR gate, and then we have a NOR gate. NOR gate is the negation of an OR gate. Okay, so the difference again is just up the head. There's a circle, small circle over here. Now, exclusive OR gate is kind of interesting. It looks like the NOR gate, or not OR gate, but you have a double curve here. Okay, that's called exclusive OR. The operations just look like this. It's a negation of A and the B, and the A and the negation of B. Okay, that's exclusive OR. Now, if we try to build a truth table for each of these gates, now this is very straightforward, right? Because this, and this, we know that. And these three are kind of new to us. And NAND and the NOR gate, they are very straightforward. But they're just a negation of AND gate and a negation of the OR gate. Okay. So now each of these gates can perform some kind of logical operation. So the way we can do this is, it's like here's the input. So for the NOT gate, so when you have input A, we have output X. Okay, so if the input is 1, then output is 0. If the input is 0, output is 1. And here, if the input depend on A and B, okay, so here's a table that we built for A and B. Okay, very straightforward, right? However, now with these logical gates, then we can build a more complicated, or very complicated, device. Okay, using the simple gates. Now you can imagine with integrated circuits like millions or billions of transistors. These transistors actually basically build various different gates, and these millions of billions of gates built together, you create an integrated circuit. That circuit is going to perform some kind of operation. Okay. Now we also have some other gates. Now these gates have a 3 input. Okay, and one output. So we will find out that these 3 input gates can be actually built easily using the 2 input gates. So, but because they're widely used, so we use a dedicated symbol to represent 3 gate input. So this is actually the 3 input AND gate. That's AND gate, and that's OR gate. Okay, that's NAND. That's NOR. Okay. So you can actually use these 3 input gates. Now, how to build the AND gate using 2 input? So you have an input A, input B, then you generate output. And then you have an input C. Combine the output of A and B, and you can build this one out. Now that's the, you can use two you can use two input AND gate. You can build up. You can build the 3 input gate AND gate. Why this is true? Because you can say A B. This is going to be A and B, right? So then A and B and C. Then you have a A and B and C. Because by using the commutative law, so you can actually, I'm sorry, it's not a commutative law, it's associate law. So you can always, combine A and B and B and C. It doesn't really matter. So that's why it's actually, you can build the so using two input AND gate, you can build a 3 input AND gate very easily. You can do the same for the OR gate. Okay, so that's why. But instead, sometimes instead of actually drawing these, 2 AND gate, you can simply using 1 AND gate. And many times you can build a multi input gate. Okay, you can do the same thing, with multiple 2 input gates. You can build a multiple input gates. So that's just a notation. Any questions? Okay, let's actually work on the next one. Now, let's actually briefly talk about how to build a NOT gate. Okay, using the transistor. Okay, you can easily build a couple of different gates using the transistor. Right? So using the transistor, you have something called a collector. That's the input. That's the emit, and that's the control. Okay. So so to build the NOT gate, you can actually do this. Okay. So in a NOT gate, if the control, because for this transistor, if the control is if the control is on, so that means the switch is on. So then the electricity gonna flow. They'll be connected. Now, if the control is off, then it will be disconnected. Okay, so the input and output will be disconnected. Now, with this, so you can basically build a NOT gate that way. So you can actually, the emit or the output, you can actually ground the output. What does ground mean?
Logic 0.
So that means the voltage is going to be 0 because you just basically drain the electricity to the ground. So so the voltage is going to drop to 0, right? So the value is going to be 0 over here. Okay, it's always 0 because it's grounded. So so that's why if the wire is grounded, then it's safe. You can touch it. You will not be executed. You know. So so then if you always ground the output side, then you can actually view the input side. Okay, so now take a look at this. You can treat the control as an input. Okay, and treat the actually collector as the output, and you always actually power the collector. So that means this side is always 1. Okay, this side is always 1. So what does that mean? So if the control is 1, so that means you connect this together. So that means so the whole thing is grounded, right? So the output going to be 1 as well. Oh, 0, because the whole thing is grounded. Now, if the control is 0, that means this one is disconnected. So that disconnected means so this side is going to be the output is going to be 1, because the output is always apply the power here. So there's a voltage. Okay. So you can treat the control as an input for the NOT gate, and this is the output. So then, so actually, so this is actually the control side, and this is the collector. The emit, the other side is always grounded. So the control basically, either connect the collector to the ground or disconnect the collector, so to keep the value 0. If the control is 0, then it's going to disconnect the collector to the ground. So that's why it just make it off and on. So depend on the control. If control is 1, the collector is 0 because it's grounded. If control is 0, then it's disconnected, so the collector can be 1. So that's basically how to achieve this operation. Now, so here's the other approach to build the NAND gate. Now, if you can build a NAND gate, then you can always build the AND gate. The AND gate is the negation of NAND gate, right? So you can build a NAND gate first. So now in this case, you can actually use 2 transistors. Transistor 1, transistor 2. Okay, so this is the collector. This is the emit for transistor 1. Okay, so this is control 1. Now the emitter for the top transistor becomes the collector of the bottom transistor. Okay, now the emitter of the bottom transistor is grounded. Grounded basically means it's always the value 0, right? Now the 2 control becomes input. So I can say A and B. Okay, now let's actually just check that one. So what about if A is 1 or A is 0, B is 0? So that means this line and this line is disconnected, because if control is 0, that means the switch is off, right? If the switch is off, and then these 2 are disconnected. Okay, here and here, they're disconnected. Okay, and if B is 0, here and here are disconnected. So that means the output will be 1, right? Actually, any one of these are disconnected. Control 1 or control, if any of these control 1 or control B are off, then it's always disconnected. So that means that if I want to build a table like this, the table gonna look like this. Here's A, B. So if A is disconnected, oh sorry. If A is disconnected, so the NAND gate always gonna be 1. If B is disconnected, it's a 1. If both A and B are disconnected, it's always 1. The only case that the NAND gate power is the output is 0 is both of these are connected. So then you connect the output to the ground, right? So only when both A are connected, B are connected, then you got a 0. So when A is 1, B is 1, then the output is 0. Any questions on this? Because that's important. Now you're going to find out, well, that doesn't look like an AND. Yes, it's not an AND, but it's a NAND gate. So it's the negation of AND. Okay, so that's a NAND gate.
Professor, how can we explain if A is 0 and B is 1?
A is 0, that means this is disconnected, right?
Disconnected. So
then anyway, the output is always disconnected with the ground.
okay.
Because you have two switch. In order to actually the grounded output, you have to make sure both controls are connected. Both controls are 1, then they are connected. Any of these are off. Any control is off, then it's disconnected. You can understand this?
If control A is off, control B is on.
Yeah.
So how can we explain that will be value 1?
Because, okay, let me actually let me eliminate this first. So I can just explain again. Okay. Okay. So let's say this is A, right?
Yep.
Okay. This is A. This is B. Now you say A is off, right?
Off.
So
0.
A is 0. B is 1, right?
Yes.
So that means this switch is connected, right?
Yes.
Now this is grounded, so it's always 0. So if this is connected, so it's a 0 here, and it's 0 here, right?
Yes.
Because they are connected. However, this is disconnected. So
Okay.
you apply the power here, so that means this is 1.
1.
Now this is 1. Now these are disconnected.
Yes.
So
Yes.
the output is 1.
1. Understood.
Okay.
Yep.
Now, in order to actually ground the output, which means in order to make the output 0, you have to make sure both A and B are 1.
1.
Then you can connect both the transistor, so
Then
you
goes
can ground
0.
the output. See, that's the idea. So that's why only one, both A is 1, B is 1, then the output is 0. Any value is 0, you're gonna disconnect the whole Y. This is actually like a serial connection, you know. Any questions? Now this actually built the NAND gate. Okay. Now it's easy to build the AND gate, right? The AND gate, because we already actually know how to build a NOT gate, so you can just put the NOT gate in the output side. So then this is gonna actually reverse the value. So this is actually gonna be the AND gate. So this is a NAND gate. Okay. So this is NAND gate, the left side. So this is how you actually build the NAND gate and the AND gate. Okay. Now, based on this, you can kind of, it's easy to see how to build the OR gate, because you can actually build this transistor in sequence. So if you cut any of this, it will disconnect the output to the ground, right? Now, the OR gate is kind of different. You can actually build like some kind of parallel connection. Okay. So now you have control 1, control B. So that's the input A and a B. Okay. Now in this case, the image side, they are connected. Okay. These are grounded. So it's 0. Okay. Now this is the power applied to the out. This is the output. Okay. So this is always, yeah. This side is always 1. So unless the output is grounded, otherwise the output is going to have the same value as 1. So let's see. Now let's discuss a various different scenario. In order to ground the output, you just need to connect one transistor, right? Either top one or bottom one, because these are parallel connection. So if either one is connected, then the output is going to be connected to the ground, right? So that means if you have a table A and B, and so if A is 1, or anyway, if both A and B are 0, so that means this is disconnected. This is disconnected. So the output is disconnected with the ground, right?
Yes, it's 1.
So that's 1, right?
1.
So it's the output get the power 1. Now, if any of these are connected, okay, so if B is 1, so that means the control B actually is applied 1. So the switch is on. So then the output is connected to the ground, right?
Yes.
So that's 0.
0.
Now, if this is a 1, it's 0. If both are 1, it's 0, right?
Yes.
So that's basically built. That's called NOR gate. Okay, because it's the opposite of the OR gate. So now to build the OR gate, the output you just need to put the negation, the NOT gate before the output. So this is gonna actually reverse the result. So then the A, B, 0, 0, then this OR gate gonna give you, its NOR gate is 1, OR gate can be 0. NOR gate is 0, 1, 1, 1. So 0, 1, 1, 0, 1, 1 to give you. So basically the OR gate gonna use basically use 1 transistor, 2 transistor, and the NOT gate gonna use another transistor. So basically it uses 3 transistors to build the OR gate. But you just need 2 transistors to build a NOR gate. Okay. Also, you just need 2 transistors to build a NAND gate, but the 3 transistors to build a AND gate. But anyway, you can use a couple of transistors to build these gates. Okay. So now it's pretty simple. Like I just as I mentioned that you can build a 3 input AND gate by using 2 input actually AND gate. So this is pretty simple. Okay. Now, after we discuss these electronic, the logical gates, okay, the very simple electronic devices. then you can combine, you can actually build a more complicated logic circuits using these gates. Okay, now eventually all these integrated circuits, they use millions or billions of these gates and build a very complicated circuit, so you can perform various different operations, and you can build up the computer processors, you can build the computer memories, you can build a computer actually other computer actually components. Okay. So because every actual Boolean function can express by algebraic expression, or in terms of truth table, the function may be expressed through the several algebraic expression. So then a Boolean function can be transformed from algebraic expression into a circuit diagram. So now you can build a logic diagram that perform these, Boolean function. Okay. It's called combinational circuits. Oh, so these circuit diagram composed of logical gates. These logical gates are connected in a particular structure. So then you can actually build this. Okay. Here's one of the example. Okay. So for this particular example we just talked about, so I have a, the Boolean actually algebra. So x, y, z is our input, and this is the Boolean algebra. And then I can build the logical circuits to simulate this Boolean function. Okay, so you have input x, y, z, right? So then, based on this, you can actually evaluate the negation of x first, right? So then you can actually using the NOT gate to build a negation of x. And then the next operation going to be negation of x and y, because by the precedence, the negation going to be the first one to evaluate, and the end going to be the next one to evaluate. So then you're going to build a negation of x and the y. So then you have an input y and negation of x going through the AND gate. So you can basically build this actually expression. And then this expression going to be added by z. It's an OR gate here. So then you can have a z and the negation x and the y, you build it together, or then you can build this logic circuit. Okay, so this is one of the example. We can build a circuit using build a logic expression using the circuit. Okay, so basically that's it. So how to simulate this? So the truth table now becomes all zero. Basically means there's no electrical flow. 0, 1, 0, that means there's no electrical flow in x and z. There's electrical flow in y. And then you can calculate what is the output. It could be 0 or could be 1. Then it's going to be defined by the truth table. Okay. Any questions on this? Now, I give you actually a couple of minutes, and I'm also going to have some probably a kind of 5 minutes break, so you can actually, do whatever you want. But before the break, I give you one of the example. So let's say if I want to define a function f of a and b, okay, it's defined like a times negation of b plus negation of a times b. Now, how to build the diagram, the circuit diagram for this algebraic, the Boolean algebra. Now, actually, this is actually the exclusive OR gate. Okay, this is the exclusive OR gate. So remember the exclusive OR gate here. Okay. Now, if you cannot remember this, let me actually go all the way back. This is actually the exclusive OR gate. So A, negation of B, and the negation of A, B. Okay. Can you build this? Can you build this logical circuit using the symbol? Okay. Let's take a small break. So let's say right now it's 9:05. Let's actually meet at 9:10. Okay, I give you let's say take a 6-minute break, and we always take a very short break so we can actually finish early. Okay, I'll be back at 9:10. Let me stop the recording.